Here's a review type question for Laplace transforms and differential equations. So it's quite a long question, and we're asked to do a few different things. First of all, we're given this function and we want to write the function g in terms of the Heaviside step function or the unit step function. Hence or otherwise, we're asked to compute the Laplace transform of g and obtain this representation. Then we're asked to use partial fractions to find the inverse Laplace transform of this. And finally, essentially, we're asked to apply the ideas to solve the differential equation and the initial value problem, I guess, in part D. So what we're going to do is we're going to work through this problem systematically. It's quite long, but I'll go through it in a step-by-step process. Okay, so the first part is connected with this function g. What I like to do with these questions is actually sketch the function first and then try to write it in terms of the Heaviside function. Okay, now let's look at this function here. It's the t function on this interval, and then it's 0 for t greater than 1. So how do we write this in terms of the Heaviside step function? Well, let me just remind you that the Heaviside step function, at least in this course, it's zero to the left of a jump point. It's 1 to the right of a jump point, A, and it's half at the jump point. Now you can see from the picture, we're not going to be able to quite describe our g in terms of our Heaviside step function at the point t equals or a equals 1. But we can. That's not going to stop us. That's not a big deal. So I think of this as g here. Okay. Now, okay. So starting at 0 and moving to the right, this part of the function is always t. And then to the right of 1, we jump back down to 0. And the function gets sort of turned off, if you like. So what we can do is start with this. But then we have to sort of take something away, so you get back to 0 after the jump point. So this is one way of doing it. Now, just for some little housekeeping, we have to exclude the point t equals 1 from our definition in this line. What we would do is define this representation at t equals 1 separately. What's the value at t equals 1 of our g? It's 1. Okay? So let's just check to make sure that that top line makes sense. This line here in our definition. To the left of 1, this is 0. So I'll just get the t function. To the right of 1, this is now t times 1. So I get t minus t, 0. So that looks good. Definitely that that's the value at the point, t equals 1. So we've got our representation. Let's see if we can take the Laplace transform now. Okay. Now, with respect to Laplace transforms, because it involves integration, if I've got this sort of point defined, just this isolated point sort of defined in one way, I can actually transform calculations. Because if you just sort of remove a point from a graph or slightly bump the point up or down, it doesn't change the integration. So essentially, we're going to be working with this. Okay. Now the Laplace transform is a linear operator, and what I would like to do here is calculate these transforms. I can calculate the Laplace transform of t. I can just go to my table. It would be 1 on s squared. But what about the Laplace transform of t times this Heaviside step function? Well, I can do it in a couple of ways. I'm actually going to use the second shifting theorem. Okay, the second shifting theorem is down here. This u of t minus c times g of t minus c equals this. Okay, so if I forget about this first term, what I would like here is something like t minus 1 times u of t minus 1. Okay, now just using a little bit of algebra, what I can do is add a term in and take a term away to get the sort of form that I would like there. So let me show you what I mean. Okay, that's the first term. That's the term I want. And the thing is, what do I need? What extra bit do I need to put in to get back to the top? Well, I've got a minus t times u, that's okay. But I've also got a positive u of t minus 1. So I want to take away a u of t minus 1. And the point is, this is an easy transform to calculate because it's in our table. Okay? So let's see if we can work out what our transforms are. The Laplace transform of t is 1 on s squared. The Laplace transform of the Heaviside step function is just this line here with c equals 1. So it'll be e to the minus s all over s. And the last thing is, let's calculate this transform here. Well, that's the second shifting theorem. This line here. So what do we need? What we do is we take the Laplace transform of little g of t and then multiply it through by an exponential. So in this setup, c would be 1. G of t, well, g of t minus c is t minus 1. So little g of t would be t. So to get this right-hand side, all I do is I take the Laplace transform of t and multiply it through by an exponential, e to the minus s in this case. So what's the Laplace transform of t? 1 on s squared. And I just multiply through by e to the minus cs, e to the minus s. Okay, so let me just write this, table and second shifting theorem. So now what I can do is get this form here. I just need to rearrange a little bit. Not bad, huh? Not bad. Okay, you can see how you need to be on top of your second shifting theorem. Okay, you probably won't have time to write down all the steps. So it would be okay to go from here to here, as long as you make sure you mention the theorem. Okay, so that's given us the form that we were asked for. Okay. The next part of this question says, use partial fractions to find the inverse Laplace transform of this particular function of s. So I think what it's asking us is to express this in a suitable form using partial fractions and then take the inverse transform of each part of those partial fractions, I guess. Okay, now there are many ways to write this in a more suitable form. My advice is to simplify whenever possible, okay? Okay, so you can see down the bottom I've got an s plus 1 and on top I've got a 1. So if I say add s into the numerator and take s away, I haven't changed it. I can bracket it up and hopefully simplify. So if I bracket it like this and form, say, two parts, you'll get the following. Now that remaining s will cancel with this. So you get something like that. Now, you can do exactly the same to this second term. Add s to the numerator, take s away. Okay, so if I again break this thing in the square brackets up into two parts, I'm going to get a minus 1 on s and then a positive 1 on s plus 1. Okay, now there are other ways you can do that. So that's the partial fraction expansion. And the point is, if we're going to use some table like this, we can find all of these functions down the right-hand side. So we can calculate each of their inverse transforms individually. Okay, so let's calculate the inverse transform of these three parts. Now again, the inverse transform is a linear operator. So we can split these things up. And calculate the three inverse transforms individually. So, the inverse transform of 1 on s squared, it's going to be t. The inverse transform of 1 on s, well, that's the first one. It's going to be 1. And the inverse transform of 1 on s plus 1, that's here with a equals 1. It's going to be e to the minus t. Okay, so now the last thing we want to do, use the Laplace transforms to solve this problem where g of t is given up here. And essentially we can use part C to help with our calculations. So it feels like we've done a lot of the hard work for part D already, and it's not going to be too bad. All right, so there is a definite method with using Laplace transforms to solve differential equations subject to initial conditions. Essentially, you take the transform of both sides, use the transform of derivatives, which are just here, and incorporate the initial conditions. You solve in the transformed state, and then you take the inverse transform of everything and get back to your solution, little y of t. So let me show you how that's done. So let's take the Laplace transform of both sides of our differential equation. Using the transform of derivatives from my table, I can simplify this. It's just going to be s of big Y of s minus little y of 0. So now I've changed from this curly L of y, little y to big Y of s, just to emphasize that we're dealing with a function of s here. This transform was calculated in part B, so it's there. Now, the initial condition was little y of 0 equals 0. So this term's actually 0. I can factorise the big Y of s plus 1s and take all the s's to the other side. So big Y of s is on the left-hand side. I've got a s plus 1 over here. I can divide that into both sides. Okay, so now we've solved in the transformed environment, in the transformed space. What we would like to do is untransform, retransform everything back to the original state and get our solution, little y of t. So that's the challenge now. Well, if we're going to take the inverse transform of these, let's use partial fractions. Well, we've already got one. This is we know the partial fractions decomposition for that because we've sort of got it up here, don't we? And we know the partial fractions expansion for this and this because we've got it there. So using parts of C, we can actually write this in a simpler form. And things simplify massively, which is nice. Okay. This was just written in this form, so let's replace that. Now, so again, just writing the expansion for this here, and this we can get from up here because that is the expansion of that. Making sure we're careful with our signs. All right, now, if you look closely in the square brackets, you get a lot of cancellation. So that cancels with that, that, and that. How good is that? So, we can calculate the inverse transforms of these easily, and the last thing we need to do is just calculate the inverse transform of this term. So we untransform everything to form our solution to our original differential equation. Now, the inverse transform of 1 on s squared, just using our table, t, the inverse transform of minus 1 on s, minus 1, the inverse transform of this, e to the minus t. And now the last thing we have to do is calculate the inverse transform of minus e to the minus s times 1 on s squared. Well, let's use our table. Okay, so we actually got these in part C, but we haven't got this yet. So it's this times e to the minus s times a function of s. So if you look here, it's the second shifting theorem. Okay, so the second shifting theorem to calculate our final transform. Big G of s would be 1 on s squared, c would be positive 1. So to apply the second shifting theorem with big G of s equals 1 on s squared, what's the inverse transform of 1 on s squared? T. Shift it and multiply by this Heaviside step function. So we'd shift it 1 unit, we would take the t function, shift it 1 unit and multiply by the Heaviside step function, u of t minus 1. So we'll get the following.